What is time? It seems like the most basic and constant thing in our lives. We feel it passing always forward, never back. It's like a giant invisible river that carries everyone and everything along at the exact same pace. We are born, we grow old, we die. The sun rises and the sun sets. It feels predictable, reliable, and above all real. But is this feeling correct? Is time a fundamental property of the universe like space or matter? Or is it a stubborn illusion? A story our brains tell ourselves to make sense of a chaotic reality? For centuries, humanity was confident we knew the answer. We believed time was a single cosmic clock that ticked at the same rate for everyone everywhere. It was absolute. Then, at the beginning of the 20th century, a young patent clerk named Albert Einstein looked at this clock and, with his revolutionary ideas, shattered it completely. He showed us that the single universal clock doesn't exist. In its place is a universe where time is personal, flexible, and deeply strange. Before Einstein, the world operated on the physics of Sir Isaac Newton. Newton's vision of the cosmos, laid out in the 17th century, was elegant and orderly. In his universe, space was a fixed, unchanging stage, and time was the universal drummer. Newton wrote that time was absolute, true, and mathematical. He meant that time flowed on its own, completely separate from space and unaffected by anything happening in space. In Newton's view, 1 second on Earth was precisely 1 second on Mars and precisely 1 second in a galaxy millions of light years away. If you could magically pause the entire universe, every clock would read the exact same time. This is common sense time. It's the time we use to schedule meetings and catch trains. It's simple and it works for our everyday lives, but Einstein was about to show that this common sense view is fundamentally wrong. Einstein's first revolution. The special theory of relativity published in 1905 began with a simple puzzle about light. Scientists had long assumed that light, like a sound wave moving through air or a ripple moving through water, must be travelling through some invisible substance that filled all of space. They called this substance the luminiferous ether. Einstein proposed a radical idea: the ether doesn't exist. Instead, he built his theory on one central immovable fact: the speed of light in a vacuum is a universal constant. This means the speed of light, roughly 300,000 kilometers per second, or 186,000 miles per second, is the ultimate speed limit of the cosmos. Here is the part that breaks our intuition. Everyone measures this speed as the same no matter how fast they are moving. If you're standing still and shine a flashlight, you measure the light beam moving at the light speed constant. If you're on a rocket ship traveling at half the speed of light and you shine the same flashlight forward, you still measure that beam moving away from you at the very same light speed constant. It doesn't add to your speed. This simple observation-backed fact has a profound consequence. If the speed of light must remain the same for everyone, then something else must change. That something else, Einstein proved, is time itself. This leads to one of the most famous concepts in physics: time dilation. In short, this idea states that the faster you move through space, the slower you move through time. To understand this, imagine a light clock. This clock keeps time by bouncing a single particle of light, a photon, between two mirrors. When the photon hits the top mirror, tick. When it hits the bottom mirror, tock. Now let's put this clock on a super fast futuristic train. For a person on the train, the clock looks normal. The light just goes straight up and straight down, tick, tock. But now imagine you are standing on the platform watching the train speed past. From your perspective, you see the light particle moving, but the clock itself is also moving forward. As the light travels up to the top mirror, the mirror has moved forward. So the light has to travel in a diagonal path. When it bounces back down, the bottom mirror has also moved forward, so it travels in another diagonal path. This diagonal path is clearly longer than the simple up and down path seen by the person on the train. But here is the key: the speed of light is constant for both of you. Since the speed is the same, but the person on the platform sees the light travelling a longer distance, that person must also observe the light clock taking more time to complete one tick-tock. From the platform, the clock on the train appears to be running slow. This isn't an optical illusion. Time itself is genuinely passing slower for the person on the train relative to the person on the platform. If the train could travel very close to the speed of light, the person on the platform might experience an entire hour, while the passenger on the train experiences only a few minutes. Motion literally stretches time. For 10 years, Einstein's theory only dealt with constant speed motion, but he knew something was missing: gravity. In 1915, he published his masterpiece, The General Theory of Relativity. This theory completely rewrote our understanding of gravity. Newton saw gravity as a mysterious invisible force that pulls objects toward each other. An apple falls from a tree because the Earth pulls it. Einstein declared this was wrong. Gravity is not a force. Instead, Einstein said gravity is the shape of space and time. He united the 3 dimensions of space and the 1 dimension of time into a single 4-dimensional fabric spacetime. He showed that massive objects like stars and planets do not pull on other objects. Instead, they warp and curve the very fabric of spacetime around them, like a bowling ball placed on a trampoline. A smaller object like a marble representing the Earth rolling nearby isn't being pulled by the bowling ball the sun. It is simply following the curve in the trampoline that the bowling ball created. That path which we see as an orbit is just the straightest possible line through curved spacetime. This curving of spacetime doesn't just affect space, it also affects time. Just as gravity can bend the path of light, it can also bend the flow of time. Einstein's equation showed that time flows more slowly in stronger gravitational fields. The closer you are to a massive object, the deeper you are in its gravity well, and the slower time ticks for you compared to someone farther away. This gravitational time dilation is not theoretical. It is a measurable fact of our universe. Scientists have used hyper-accurate atomic clocks to prove it. If you place one clock at sea level and another on top of a mountain where gravity is slightly weaker, the clock on the mountain will in fact run slightly faster. The difference is minuscule, but it is real. Your head is aging slightly faster than your feet. A perfect everyday example is the GPS global positioning system in your car or phone. The GPS network relies on dozens of satellites orbiting high above the Earth. These satellites are moving very fast, which due to special relativity makes their clocks run slow, but they are also far away from Earth's gravity, which due to general relativity makes their clocks run fast. The gravitational effect is the stronger one. Combined, their clocks tick about 38 microseconds faster every day than clocks on the ground. This sounds tiny, but if the engineers didn't build Einstein's equations into the system to correct for this, time bending the entire GPS network would fail. Your location data would be wrong by several miles within a single day. The movie Interstellar provided a dramatic and largely accurate visualization of this. When the astronauts landed on Miller's planet, which orbited extremely close to a massive black hole, they were deep in an immense gravity well. Time on that planet was stretched almost to a breaking point. For every 1 hour they spent on the surface, 7 years passed for their crewmate orbiting safely far away. When they returned to their ship, they had barely aged, while their friend was decades older. Einstein, with his 2 theories, destroyed the idea of a single absolute clock. He gave us a universe where time is relative, elastic and personal, a universe where your speed and your location in a gravitational field fundamentally change the pace at which you experience reality. We have seen how moving fast through space actually slows down the passage of time. This effect, called time dilation, is not an illusion. It is a fundamental feature of our universe. But this idea leads to one of the most famous and confusing thought experiments in all of physics, the twin paradox. Let's imagine 2 twins, identical in every way. We will call them Eartha and Astro. Eartha decides to stay on Earth living her normal life. Astro, being the more adventurous twin, becomes an astronaut. He is given a mission to travel in a new incredibly fast starship to a nearby star system, let's say Proxima Centauri, which is about 4 light years away. His ship is a marvel of engineering, able to travel at 80% of the speed of light. Astro says goodbye to Eartha, gets in his ship and blasts off. He accelerates to 80% of the speed of light, cruises to the star system, slows down just long enough to take some pictures, then turns around. He accelerates again to 80% of the speed of light for the return trip and finally decelerates to land safely back on Earth. When he steps out of his ship, he is greeted by his twin sister Eartha, but he is shocked. While only a few years have passed for him, decades have passed for Eartha. She is now an old woman while he is still relatively young. Astro's clock, his biology, his aging process, everything in his ship ran slower than on Earth. This by itself is a straightforward example of time dilation. So where is the paradox? The paradox arises when you try to look at the situation from Astro's point of view. Einstein's first rule of special relativity is that all non-accelerating motion is relative. This means that from Astro's perspective inside his ship while he's cruising at a steady speed, he is sitting still. When he looks out of his window, he sees Earth and his twin, Earth, flying away from him at 80% of the speed of light. Then he sees Earth slow down, turn around and come back toward him. If all motion is relative, shouldn't Astro see Earth's clock running slow? If that were true when they reunited, Astro should expect to find that Eartha is the younger twin. Both twins cannot be younger than the other. This is the heart of the paradox. It seems to break the very rules of relativity. The solution to the paradox, the reason Astro is definitively the one who ages less, lies in one critical word: acceleration. The rule that all motion is relative only applies to inertial frames of reference. An inertial frame is one that is moving at a constant speed in a straight line, without speeding up, slowing down, or turning. Let's look at the two twins again. Eartha, remaining on our planet, is in mostly a single inertial frame. She is just floating along with Earth. She never feels any forces pushing her into her chair. We are ignoring Earth's gravity and rotation for this experiment, as they are tiny effects compared to the spaceship. Now look at Astro. His journey is not symmetrical with Eartha's. To leave Earth, he must accelerate powerfully. He feels a massive force known as G-force pinning him to his seat. To stop at the distant star, he must decelerate, firing his engines to slow down. To come home, he must accelerate again in the opposite direction. And finally, to land on Earth, he must decelerate one last time. Acceleration is not relative. It is absolute. You know when you are accelerating, you feel it. If you are in a windowless room, you cannot tell if you are sitting still or moving at a constant 1 million miles per hour. But you can instantly tell if you hit the brakes or step on the gas. Because Astro is the one who undergoes acceleration, the symmetry is broken. He is the one who changed his motion, who switched from one inertial frame moving away to another moving back. Eartha stayed in her home frame the entire time. General relativity. Einstein's later theory is the one that fully describes gravity and acceleration, and it confirms this. The person who feels the g-forces, the one who accelerates, is the one whose clock will be slower compared to the twin who did not. Therefore, there is no paradox. The situation is not symmetrical. Both twins agree that Astro was the one who fired his rockets and felt the push of acceleration. Astro is the traveller, and the traveller always ages less. The time he spent accelerating and decelerating combined with the time spent cruising results in less total time passing for him than for Eartha. This solution that acceleration breaks the symmetry is correct, but it doesn't fully explain how time gets so mismatched. The deeper, more mind-bending reason lies in a concept called the relativity of simultaneity. This is the idea that the very concept of now is relative. We instinctively believe that there is a single universal now that everyone in the universe shares. We think that if it is 300 p.m. on Earth, we can say that at that exact same moment something is also happening on Mars, and something else is happening in the Andromeda galaxy. We assume time flows at the same rate for everyone. Einstein proved this is wrong. Whether two events happen at the same time simultaneously depends entirely on how you are moving. Imagine a very long, very fast train moving past a platform. A woman, let's call her Mavis, is standing perfectly in the middle of the platform. A man, Morty, is sitting perfectly in the middle of the train car. Just as Morty passes Mavis, two lightning bolts strike at the same time from Mavis's perspective. One bolt hits the very front of the train car, and the other hits the very back. Since Mavis is in the middle of the platform, the light from both flashes travels the same distance to her eyes and arrives at the exact same moment. She sees them as perfectly simultaneous. But what does Morty on the moving train see? He is also in the middle of the train car, but he is moving toward the light from the front strike and away from the light from the back strike. Because the speed of light is constant for all observers, the light from the front bolt reaches Morty's eyes first, before the light from the back bolt catches up to him. For Morty, the two events were not simultaneous. He saw the front of the train get hit, and then a moment later he saw the back of the train get hit. Who is right, Mavis or Morty? They both are. There is no universal now. Their now depends on their motion. Let's apply this to the twin paradox. While Astro is cruising away from Earth, he and Eartha have different definitions of now. On his outbound journey, he sees Eartha's clock running slow time dilation. But here is the key: when Astro turns around at the distant star, he has to accelerate. This act of decelerating and accelerating in the other direction forces him to change his entire frame of reference. When he changes his reference frame, his plane of simultaneity, his definition of now back on Earth swings wildly. During that very short U-turn, Astro's now slices through a huge amount of time on Earth. In his new inbound reference frame, Eartha and all of Earth has suddenly aged by many years. Then as he cruises back home, he once again sees Eartha's clock running slow. So from Astro's perspective, outbound trip Eartha ages slowly. The U-turn Eartha ages very, very rapidly in his new now. Inbound trip Eartha ages slowly again. From Eartha's perspective, it's much simpler. She just sees Astro moving away and his clock runs slow. Then she sees him moving back and his clock still runs slow. The light from his ship will be shifted, but the fundamental rate of his clock is slow for her entire journey. When they meet, both of their observations add up to the same single reality: Astro is younger. The relativity of simultaneity explains how their clocks, which both saw as running slow, could end up with such different readings. All of these strange effects, time slowing down, lengths contracting and now being relative, can feel like a set of strange, disconnected rules. But they are all symptoms of a single profound truth. We do not live in a universe of three-dimensional space and a separate one-dimensional time. We live in a four-dimensional space-time. This was the great insight of Einstein's former teacher Hermann Minkowski. He realized that space and time are woven together into one seamless fabric. This four-dimensional 4D fabric is the stage on which all events in the universe happen. A helpful analogy is to think about motion in a different way. Everything in the universe is always traveling through this four-dimensional space-time at one constant speed, the speed of light. If you are standing perfectly still reading this, you are not moving through the three dimensions of space: left, right, forward, backward, up, down. Because you are not using any of your motion budget on space, all of your motion is directed through the fourth dimension time. You're traveling through time at the maximum possible speed, 1 second per second. Now imagine you start walking. You have taken some of that motion budget that was pointed purely through time and you have rotated it slightly to move through space. Because you're now using some of your speed to move through space, you have less speed available to move through time. Your clock, compared to a stationary person, ticks just a tiny, tiny bit slower. If you get in a car, you're rotating your motion even more into the space dimensions, and your time slows down even more. If you are astro traveling at 80% of the speed of light, you are using a massive amount of your motion budget just to move through space. This means you have very little speed left for moving through time. As a result, your time slows down dramatically. If you could, which you cannot, accelerate to 100% of the speed of light, all of your motion budget would be used for moving through space. You would have no speed left for moving through time. For you, time would stop completely. A photon, a particle of light, experiences no time at all. From its perspective, it is emitted and absorbed at the exact same instant, even if it has to cross the entire universe. This space-time fabric solves the twin paradox perfectly. In space-time, Earth's path is a mostly straight line through the time dimension. Astro's path is bent. He travels out through space and then back through space, creating a triangular-shaped path through space-time. In the weird geometry of space-time called Minkowski geometry, a straight line is actually the path of the longest possible time. The bent path that Astro took is a shortcut through time. Because Astro took the bent path through space-time, he travelled a shorter distance through time than Earth did. When they meet again at the same point in space, they are also meeting at the same point in time, but to get there, Earth took the long way, a straight line, experiencing maximum time, while Astro took the shortcut, a bent path, experiencing minimum time. The paradox disappears and we are left with a new unified and flexible reality, a four-dimensional space-time. In the previous sections, we explored time as a physical property of the universe, a vast and rigid structure governed by the laws of physics. We looked at time as a dimension, a river flowing in one direction measured by the precise ticking of atomic clocks and defined by the equations of Albert Einstein. This is clock time, or chronos. It is cold, impersonal, and for the most part stable. It marches forward indifferent to our human lives, but we all know there is another kind of time. This is the time we feel. This is the internal clock, or psychological time. It is not measured in seconds, but in experiences. It is not rigid. It is elastic, pulling and stretching based on our emotions, our attention, and our memories. This is the time that truly governs our lives. It is the time inside our heads. This internal time is a completely different phenomenon from the time on the wall. Physical time is measured by the decay of a cesium atom. Psychological time is measured by the density of a memory. The physics of Einstein can explain why a clock on a satellite ticks at a different speed from one on Earth, but it cannot explain why an hour in a dentist's chair feels like a lifetime, while an hour with a beloved friend feels like a moment. To understand this, we must look away from the cosmos and into the human mind. Physical time is consistent. A minute is always 60 seconds. Psychological time is relative. The clock in our head is not a reliable instrument. It is a storyteller. It speeds up, slows down, and sometimes it seems to stop altogether. Our perception of time is not a passive reading of a clock, it is an active creation of our brain. A simple example is the watched pot scenario. If you are waiting for a very important email, the 2 minutes it takes to arrive can feel agonizingly long. But if you are lost in a fascinating book, 2 hours can disappear in what feels like a blink. The physical time is fixed, but the felt time is wildly different. This is because psychological time is not built from seconds, but from what our brain chooses to pay attention to. The most common way we experience this distortion is through the density of our experience. Time seems to stretch or shrink depending on what we are doing, and more importantly, how we feel about it. When we are bored, anxious, or in pain, time slows to a crawl. Think of a person stuck in a traffic jam late for an important meeting. Every second is amplified. Their attention is focused entirely on the passage of time itself. They are watching the clock literally or mentally. Because their brain is not processing new or interesting information, it is just waiting. Each moment feels empty and heavy. This empty period feels long. The same is true for anxiety. When you're waiting for bad news or for a frightening event to happen, your brain enters a state of high alert. You become hyper-aware of the present moment, and this intense focus on the now makes it feel like it is stretching out, lasting far longer than it should. The exact opposite happens when we are completely immersed in an activity. This state is often called flow, a concept described by the psychologist Mihai Csikszentmihalyi. This is the feeling you get when you are in the zone. It could be while playing a musical instrument, competing in a sport, writing a story, or even having a deep, engaging conversation. In a state of flow, you're so absorbed in the task that your sense of self seems to melt away. You're not thinking about your problems, you're not thinking about the future, and crucially, you're not thinking about time. Your brain is processing a massive amount of information related to the task, and it dedicates all its resources to it. The part of your brain that acts as an internal timekeeper is effectively silenced, because you are not logging the passage of the minutes they slip by unnoticed. It is only when you finally break your concentration and look at a clock that you are shocked to find that 3 or 4 hours have passed. Time flies when you're having fun, not just because you're happy, but because your attention is directed away from time itself. This relationship between our brain and time explains one of the most common and puzzling human experiences, the feeling that time speeds up as we get older. We all ask, where did the year go? The answer seems to be a combination of novelty and habit. Think back to your childhood. Summers felt like an eternity. A single school year felt like a lifetime. This is because for a child, the world is saturated with novelty. Almost everything is a first. The first time riding a bike, the first day of school, the first time swimming in the ocean, the first time making a new friend. The child's brain is in a constant state of high-intensity recording. It is absorbing and storing a massive amount of new, detailed information. When we look back on that time, our memory is dense with these unique markers. That summer is not one single memory. It is a collection of thousands of small, distinct, and emotionally charged events. Because the memory is so full, the period of time itself feels vast and long. Now consider adult life. As we age, we develop routines. We drive the same route to work. We have the same tasks to do. We eat similar foods, talk to the same people, and fall into predictable patterns. Our brain, which is a masterpiece of efficiency, recognizes these patterns. It stops recording the details because it doesn't need to. It already knows this script. The daily commute is no longer a unique experience, it is just the commute. The brain chunks these routine experiences into a single file. When we look back on a week, a month, or a year of this routine, our memory is thin. The days blur together because there are very few unique memory markers to separate them. Monday was the same as Tuesday, which was the same as Wednesday. Because the memory file for this year is so compressed and lacking in detail, the period of time feels short. Time seems to be accelerating because our brains are getting more efficient at ignoring it. This is why travel, learning a new skill, or actively breaking our habits can slow down time. It forces our brain out of autopilot and back into record mode, creating the new dense memories that make time feel full again. This elasticity of time becomes most pronounced in extreme states of consciousness. Under severe stress or in deep meditation, the internal clock can behave in ways that defy all logic. One of the most dramatic examples is slow motion perception during a traumatic event. People who have been in car accidents or soldiers in combat frequently report that the event unfolded in bullet time. They describe seeing the glass shatter piece by piece, or watching an object move through the air as if time had slowed down. It is not that time actually slowed down for them, or that their brains were thinking faster like a superhero. The leading theory is that this is a trick of memory. During a life-threatening event, the brain's survival system, specifically a region called the amygdala, kicks into overdrive. It screams, "Record everything, this is important for survival." The brain then captures an incredibly dense amount of sensory data in those few seconds. It is like a camera that suddenly switches from taking 24 pictures per second to taking 1,000 pictures per second. The event itself is over in an instant. But when the person plays back the memory, it is so rich with detail, so packed with frames, that it feels as if it must have taken much longer. The memory of the event is in slow motion, so the experience of the event is remembered as slow motion. A completely different kind of distortion happens in deep meditation. Here the goal is not survival, but the opposite, a complete release of struggle. Many forms of meditation train the practitioner to focus all their awareness on the present moment, the now. Instead of worrying about the future or ruminating on the past, the mind is anchored to a single point, like the feeling of the breath or a sound in the room. When this is achieved, something remarkable happens. The internal narrative of past, present, future dissolves. The constant mental tick-tock of the clock fades away. Time stops feeling like a river flowing from one place to another, and instead feels like a deep ocean that you are floating in. It is not slow in the way boredom is slow. It is expansive. The present moment, the now, feels infinite. This is an experience of timelessness where the clock on the wall becomes completely irrelevant, and the person experiences a sense of deep, profound stillness. Ultimately, our experience of time is not a fixed measurement, but a flexible narrative. Our internal clock is a storyteller, and its stories are deeply influenced by our emotional state. Time is elastic, stretching and shrinking to fit the contours of our feelings. The most bizarre and lawless version of this is time in our dreams. When we are asleep and dreaming, the logical timekeeping part of our brain, the prefrontal cortex, is quiet. The emotional and memory-based parts of the brain are highly active. In a dream, time is completely shattered. You can be a child in one scene and an adult in the next. An entire complex adventure that feels like it lasted for days can be packed into a 5-minute cycle of REM, rapid eye movement sleep. Time in a dream is not linear. It is associative. It jumps based on feelings and memories, not on the laws of cause and effect. In our waking lives, love is a powerful time distorter. When falling in love, time can fly. Those first long conversations that last until 3 a.m. feel like they only lasted an hour. But love also creates density. That first month of a new relationship filled with new experiences, intense emotions and high novelty can feel as long and significant in retrospect as an entire year of normal routine life. And the anticipation of seeing someone you love can make time slow to a painful crawl. The most painful distortion of all is time in depression. For a person experiencing severe depression, time does not just slow down, it stops. It becomes a prison. Depression is often characterized by a complete loss of pleasure and hedonia and a feeling of hopelessness. The future appears to be a grey, empty and unchanging extension of the present. The present moment itself feels heavy, empty and meaningless. Because there is no novelty, no joy and no hope to create new positive memories, the brain has nothing new to record. Time stops being a flowing river and becomes a stagnant pond. Every day feels exactly the same as the last. It is the terrifying experience of being trapped in a single, never-ending, colourless moment. This shows us that the clock on the wall, the one governed by physics, is only half the story. It may measure the duration of our lives, but it is our internal clock, our brain, our emotions, our attention and our memories that defines the quality and experience of that life. Time is not just something that happens to us, it is something we create. This is one of the most profound and personal questions in all of physics. At the most fundamental level, the laws that govern reality, like gravity or the interactions of tiny particles, do not seem to care about the direction of time. They are time-symmetric. If you watch a video of a single planet orbiting a star, you cannot be certain if the video is playing forward or backward. The orbit looks perfectly normal either way, but our lives are not like that at all. We live in a world governed by a strict one-way street. We feel ourselves being pushed from a past that we can remember into a future that is unknown. We have photographs, history books, and scars on our skin, all of which are detailed records of what has been. We have no such records of what is to come. We can make predictions about the future, often with great accuracy, but this is entirely different from remembering it. This feeling of a one-way flow is often called the psychological arrow of time. It is rooted in this process of cause and effect. A memory is a physical state in your brain, a complex pattern of connected neurons. That pattern is an effect. Its cause was a past event, an interaction with the world, a sight you saw, a sound you heard. Because cause must always come before effect, we can only have memories of things that have already happened. We cannot have a memory and effect of a future event, a cause that has not yet occurred. This fundamental asymmetry that the past is fixed and recorded, while the future is open and unknown, is the most immediate and personal arrow of time we experience. This psychological arrow of time, our very sense of memory and causality, is not a separate magical property of consciousness. It is a direct consequence of a much deeper, more fundamental physical law, the second law of thermodynamics. This law introduces the concept of entropy, which is a precise scientific measurement of disorder, randomness, or decay. The second law is one of the most ironclad laws in the universe, and it states a simple, profound truth in any closed system. The total amount of entropy disorder will always increase over time. It never ever goes down. The classic example is the one you mentioned, a fresh whole egg. This egg is a marvel of complex ordered information. It has low entropy. The yolk is perfectly separate from the white, its complex proteins are folded in specific ways, and everything is contained within an organized shell. Now let's introduce an event. You drop the egg. It shatters on the floor, mixing the yolk and white into a scrambled mess, scattering shell fragments. This new state is highly disordered. It has high entropy. The second law explains why this process is a one-way street. The universe always moves from order to disorder. Why don't we see the reverse? Why doesn't the splattered mess on the floor ever spontaneously gather itself, separate the yolk from the white, and leap back into your hand as a perfect unbroken egg? The basic laws of motion for each individual molecule would allow it. But the probability is the key. There is essentially only one way for all those billions of atoms to be arranged as a perfect egg. But there are trillions upon trillions of ways for them to be arranged as a broken mess. The universe simply moves toward the state that is most probable, which is always the state of greatest disorder. The arrow of time is nothing more than the universe obeying this statistical law and falling into chaos. This brings us to the single greatest mystery in all of cosmology. If the universe is constantly moving from a state of order low entropy to a state of disorder high entropy, then it logically follows that the universe must have begun in a state of the most perfect, incredible order imaginable. This is the problem of the Big Bang. We tend to think of the Big Bang as a chaotic explosion, but in thermodynamic terms it was the complete opposite. It was a state of unimaginably low entropy. All the matter and energy of the entire observable universe was compressed into a space smaller than an atom. But it was not just compressed, it was unbelievably smooth and uniform. This perfect smoothness was a state of profound order. Think about it this way: gravity likes to pull things together. A smooth, even distribution of gas in space-low entropy is an unstable arrangement. Over time, gravity will inevitably pull that gas into clumps, forming dense stars and galaxies, leaving behind vast cold voids of empty space. This clumpy universe of hot stars and cold voids is gravitationally much more disordered higher entropy than the smooth soup it began as. The Big Bang, therefore, was the perfect egg. The entire 13.8 billion year history of the cosmos has been the story of that egg breaking, of stars forming living and dying, and of energy spreading out and cooling down, all in accordance with the second law. The question that haunts physicists is why? Why did the universe begin in this pristine low entropy state? The second law explains why the clock unwinds, but it cannot explain who or what wound up the clock in the first place. This entire discussion of time, flowing or moving leads to a radically different and very unsettling alternative idea. What if time doesn't flow at all? This concept, born from Einstein's theories of relativity, is often called the block universe or eternalism. Einstein's theories united space and time into a single four-dimensional fabric called space-time, 3 dimensions of space plus 1 of time. This theory of the block universe suggests that we should treat time just like we treat space. You would never say that only the present location exists. You know that other places like Paris or the moon exist right now, even if you are not at them. This theory applies the same logic to time. It suggests that the past, present, and future all exist with equal reality as a complete, unchanging, 4-dimensional block. Your birth this moment, you're reading this, and every moment in the future are all just different coordinates on this space-time block. The analogy is a reel of film. For the characters living inside the movie, the story unfolds one frame at a time. They experience a present moment, remember the past frames, and wonder about the future frames. But for us, the projectorist, we can take the film reel off the projector. We can hold the entire movie in our hands and see the beginning, middle, and end all at once. In this view, our sense of now is just a subjective illusion. Our consciousness is like a spotlight moving along this static film reel, illuminating one frame at a time, creating the feeling of passage. This is a profound and deeply counterintuitive idea. It suggests that the future is not open, but is already there, just as fixed and real as the past. So where does this leave us? Is the arrow of time a real objective feature of the cosmos, or is it just a subjective illusion of our consciousness? The answer is likely a subtle mix of both. The feeling of time flowing that now is a special moving moment is almost certainly a subjective psychological phenomenon. It is a product of our brains, which are physical systems that process information in a linear causal way. However, the direction of time, the profound asymmetry between past and future, appears to be an objective physical reality. This direction is given to us by the second law of thermodynamics. The thermodynamic arrow entropy points from the past low entropy to the future high entropy. Our psychological arrow memory and causal arrow, cause before effect, are forced to align with it. We can only build memories, create new local order in our brains by expending energy and creating more total disorder entropy in the universe, such as by releasing heat. We are quite literally entropy-creating machines. Therefore, we must remember the past, the more ordered state, and not the future, the more disordered state. The flow of time might be an illusion, but the direction of time is as real as the universe itself, written into the statistical laws of physics. It is the unwinding of the primordial clock, the breaking of the cosmic egg. Time as temperature. A non-fundamental property. When we think of the most basic ingredients of the universe, we usually think of things like space matter, and of course time. We imagine time as a fundamental river, a cosmic conveyor belt that carries all of reality forward from the past through the present and into the future. But in the last few decades, a radical idea has taken hold in theoretical physics. What if time isn't fundamental at all? What if time is an emergent property, something that arises from a deeper timeless reality, much like temperature arises from the behavior of atoms? This is a strange comparison at first, so let's break it down. Think about a hot cup of coffee. You can feel its heat. You can measure its temperature, perhaps 100 degrees Fahrenheit. But what is that temperature? If you could zoom in all the way down to the individual water molecules in the cup, you would find that not a single molecule has a temperature of 100 degrees. It's a meaningless concept at that tiny scale. Instead, what you would see are trillions of molecules zipping around. Some are moving very fast, some are moving slowly, and most are somewhere in between. The temperature we feel is not a property of any one molecule. It is the average kinetic energy of all the molecules combined. It is a statistical effect bulk property. It is a useful, real and measurable description of the collective system, but it is not a fundamental property of the parts. You cannot have a temperature with just one molecule. The time as temperature idea suggests that time itself works the same way. At our level, the macro level of people and planets' time flows undeniably. Clocks tick things age, and we feel a clear and irreversible arrow of time. But what if, just like with the coffee, we zoomed all the way down? What if we could look at the most basic pixels of reality, the atoms of space-time itself, perhaps at the incredibly small Planck scale, a length so small it's written as a decimal point, followed by 34 zeros and then a 1. According to this hypothesis, at that fundamental microscopic level, the concept of time might cease to exist. There might be no flow, no past, and no future. There might only be a complex web of quantum interactions and events existing all at once in a static block. So where does our flow of time come from? It emerges in the same way temperature does, through statistics and averaging. We are large complex systems made of countless particles. We are not single molecules of reality. We are the entire cup of coffee. Our experience of time's flow, the very ticking of the universal clock, might be a consequence of our scale. It might be the statistical average of all those countless timeless quantum events. Just as temperature emerges when you have many particles, time emerges when you have a complex universe. This idea is profound because it changes what we are looking for. For centuries, physicists have tried to find the particle of time, sometimes called a chronon, thinking it must be a fundamental building block. But if time is like temperature, that search is pointless. You will never find the particle of heat in a cup of coffee. You will only find molecules in motion. This hypothesis tells us to stop looking for time itself in the basement of reality. Instead, it tells us to look for the timeless components, the molecules of the universe, and figure out how their collective behavior gives rise to the illusion, or rather, the emergence of flow. The following theories are all in their own way attempts to do just that. They are proposals for what those timeless molecules are and how they conspire to create the river of time, the timeless quantum world loop, quantum gravity Carlo Rovelli. If time is not fundamental, then what is one of the most compelling and poetic attempts to answer this question comes from a theory called loop quantum gravity, or LQG. One of its most prominent voices, the physicist Carlo Rovelli, paints a picture of the universe that is both startling and beautiful, a universe built not of things moving in time, but of processes relating to other processes. LQG proposes that space itself is not a smooth empty container. Like matter, space is quantized. It is made of discrete indivisible units. You cannot have half a unit of space. There is a smallest possible volume. You can picture these atoms of space as tiny fundamental loops, all woven together in a complex network or spin foam. This network is space. It doesn't live in space, the network creates space. Now here is the crucial step. When Rovelli and other physicists wrote down the core equations to describe the behavior of this network, the fundamental physics of the universe, they ran into a famous and terrifying problem. In the most fundamental equation of loop quantum gravity, the variable for time simply vanishes. It's not there. The equation known as the Wheeler-DeWitt equation doesn't describe how the network evolves in time. It just describes the network's state, period. It's a static, timeless description of reality. This discovery is known as the problem of time, and it is either a catastrophic failure of the theory or its single greatest insight. Rovelli argues passionately that it is the latter. He insists we must take the equation at its word. Fundamentally, there is no time. There is no master clock, no conductor's baton keeping the beat for the rest of the cosmos. So how does anything happen? Rovelli's answer is that time is relational. We don't need a master clock because things can just keep time relative to each other. Imagine an orchestra without a conductor. How does the music happen? The first violinist doesn't look at a conductor. She listens to the cellist. The drummer doesn't follow a baton. He watches the first violinist. The flutist keys off the drummer. The music, the event, emerges from the relationships and interactions between the players. This, Rovelli says, is our universe. The fundamental reality is not things, it is events or processes. A thing is just a process that is temporarily stable like a standing wave in a river. We as human beings are not things. We are a complex collection of processes, our metabolism, our neural activity, our breathing. We are a long continuous event. When we experience time, we are not sensing some external universal flow. We are simply one set of processes interacting with another. When you look at a clock on the wall, you're not measuring time. You're quite literally comparing one process, the clock's gears turning, with another process, your brain's neurons firing. When we as a society measure a year, we are not measuring a unit of absolute time. We are counting one process, the Earth completing an orbit relative to another, the sun's apparent position. In this view, the universe is a vast interconnected network of events, each piece happening only in relation to the others. Time is not the grand stage on which this happens. Time is the happening itself. It is the dance, not the ballroom. The flow we feel is simply our limited local perspective as one of the dancers moving in step with the partners nearest to us. At the fundamental level, there is only the timeless, static choreography of the entire cosmic network. Relational time, the Page-Wouters mechanism in time emerging from correlation. Carlo Rovelli's idea of a relational, conductorless orchestra is a powerful philosophical picture. But can this idea be made mathematically precise? Can you really get a world that looks like it's moving and evolving from a universe that is fundamentally static? In 1983, two physicists named Don Page and William Wouters proposed a brilliant and bizarre mechanism that showed exactly how this could be possible. It's known as the Page-Wouters mechanism, and it's one of the most important ideas in quantum gravity. It argues that our experience of time emerges from quantum correlation, a concept better known as entanglement. Here is the setup. It requires two big leaps of faith. First, you must accept that the entire universe, everything including you, me, the clocks, and the distant galaxies can be described by a single colossal quantum wave function. Second, you must accept that this total wave function is static and timeless. It does not evolve. Nothing happens. The universe as a whole just is. This is the block universe we discussed it before, a frozen snapshot of all reality. This is where Page and Wouters got clever. They said, okay, the total universe is frozen, but what we experience is never the total universe. We are by definition parts of the universe observing other parts of it. So they proposed, let's mathematically split this frozen universe into two pieces, the system. This is the part of the universe we want to observe. Let's say it's a cat in a box, the clock. This is the rest of the universe. Or more simply, it could be just one other part of the system we use as our reference, like an actual clock. In this static, frozen total state, the system, the cat, and the clock are not independent. They're entangled. Their states are linked or correlated. This is the key. Even in a frozen picture of a horse race, you can see correlations. You can see that the horse Seabiscuit is correlated with the 5-furlong pole, while the horse War Admiral is correlated with the 4-furlong pole. The picture itself isn't moving. But by comparing the state of one part, the horse, to the state of another part, the track markers, you can reconstruct a story. You can deduce that Seabiscuit is ahead of War Admiral. The Page-Wouters mechanism is the quantum version of this. They showed that if you as an observer only look at the system, the cat, and forget about the clock and the total state, the only way you can describe what you see is by using the normal time-dependent laws of physics. The cat appears to evolve to be alive or dead to change. In other words, the flow of time is a perspective effect. It's what you get when a timeless entangled system is split into an observer and the observed. Time in this model is the dictionary that translates the state of the system into the state of the clock. The laws of physics that we use every day, which all depend on tea time, just a fantastically useful handbook for describing these correlations within the static block. This is a revolutionary concept. It means that time does not cause change. It means that the fundamental change is just a set of static correlations between the parts of the universe. We experience this correlation as a flow because we are one of the parts. We are a clock reading another system. We are the horse Seabiscuit, and as we look around we see the track markers, our clock correlated with our position, and it feels like we are racing forward when in fact we are all just part of one giant timeless frozen photograph. Time from quantum entanglement information as the source of flow. The Page-Wouters mechanism gives us a powerful hint. If time emerges from correlation, then perhaps the real fundamental ingredient is not matter or space or time. Perhaps it is information. This line of thinking has exploded in the last 2 decades, leading to the it from qubit principle. This is the idea that the universe is at its core a form of quantum computer. The fundamental bits of reality are qubits, units of quantum information, and the stuff that connects them all, the glue that holds reality together, is quantum entanglement. Entanglement is the spooky action at a distance that Einstein famously distrusted. It's a quantum connection between 2 or more particles. If 2 particles are entangled, they behave as a single system even if they are on opposite sides of the galaxy. Measuring one instantly influences the state of the other. It is the most profound and strangest feature of quantum mechanics. So how do we get time from this? If the universe is just a static network of entangled qubits, where does the flow come from? The modern answer builds on the Page-Wouters idea. The flow is an artifact of how we as observers process this information. Imagine yourself as a tiny part of this vast quantum network. You are a collection of qubits. To know anything about the world around you, you must interact with it. This interaction creates entanglement between you and your environment. When you look at a tree, your brain's qubits become entangled with the tree qubits. You have now recorded information. The flow of time in this view is the process of you becoming progressively more entangled with the rest of the universe. This provides a powerful explanation for the arrow of time, the fact that time only flows in one direction. Why? Because entanglement is typically an irreversible process. Once you become entangled with your environment, once you learn something or observe something, it is exceptionally difficult to unentangle. It's like trying to get a drop of red dye out of a glass of water after you've already stirred it in. The past, therefore, is just the set of things you're already entangled with. Your memory is your environment. The future is the set of things you are not yet entangled with. And the present moment is the boundary of that entanglement, the action of you becoming newly correlated with the world moment by moment. Time is the spreading of information. Its one-way direction is simply the one-way street of information spreading and entanglement growing. This is deeply connected to the concept of entropy disorder, which also only ever increases. In this modern view, entropy and entanglement are almost the same thing. The arrow of time is just the arrow of entanglement. This idea is not just philosophy. It has become a central tool in theoretical physics, especially in understanding black holes. A breakthrough known as the holographic principle and the ADS-CFT correspondence showed mathematically that the very geometry of spacetime can be built from patterns of entanglement. More entanglement literally creates more space. In this model, time and space are not the stage, they are the information. They are the pattern of spooky connections that link the fundamental now of the universe together. The thermal time hypothesis time emerging from the statistical state of a system. This brings us full circle back to our first idea, time as temperature. The thermal time hypothesis is perhaps the most precise and powerful statement of this concept. It was proposed by Carlo Rovelli and the mathematician Alain Connet. It makes a bold and sweeping claim time does not cause things to be thermal, hot-cold in equilibrium. Rather, the thermal state of a system generates its own time. This is a subtle but crucial difference. Let's revisit our box of gas. Normally we think of it like this. We have a box of gas. We let time pass. As time passes, the gas molecules spread out and the box eventually reaches a stable, boring, thermal equilibrium state, where everything is evenly distributed. In this view, time is the independent variable that drives the system toward this state. The thermal time hypothesis flips this script completely. It says forget about any external universal time, just look at the state of the system. A physical system like our box of gas or the entire universe has a statistical state. This is just a description of the average properties of all its microscopic parts. The hypothesis claims that any system in a thermal equilibrium state automatically defines its own flow of time. The flow is a mathematical property of the state itself. It is a heartbeat that emerges from the statistics of the system just as temperature does. This thermal time is not a universal clock, it is local to that system. This is the most mind-bending part. If you have two different systems that are not interacting, say you in your room and a black hole light years away, they are each in their own thermal state. According to this hypothesis, they would each generate their own thermal time. Your flow of time, driven by the statistics of your brain and body, would have no relationship to the flow of time for the black hole. The time we feel, the 1 second per second flow, is not the time of the universe. It is the thermal time of our own thermodynamic biological system. It is the music generated by the statistics of our own orchestra. So when we look out at the universe, we are projecting our own local thermal time onto it. We assume the whole cosmos is ticking to our beat, but this is just an illusion. The universe itself in this view is a vast, timeless quantum state, but it's a state full of subsystems like us and stars and black holes that are in thermal contact with their environments. Each of these subsystems generates its own local time, and what we call time is simply the one that emerged from the statistical mechanics of the stuff we are made of. This is the ultimate vanishing act. The foundation of time doesn't just crack, it dissolves. It is replaced not by a new deeper foundation, but by a web of statistics, information, and relationships. Time is not the master of the universe. It is a reflection of the universe. It is the byproduct of a complex system looking at itself. And for many physicists, this is the only way we can finally make sense of a world that is at its deepest level, utterly, profoundly timeless. Our most basic human intuition, the one we trust above all others, is the feeling of now. We feel the present moment as a special illuminated point in reality. The past feels finished, a fixed memory, while the future feels open, a void of possibilities waiting to be born. We feel time flow like a river, carrying us from one now to the next. But what if this fundamental experience is a profound illusion? When we turn to physics to find this special now, we discover it isn't there. The laws of physics, particularly Albert Einstein's theories of relativity, completely dismantle this idea. Einstein showed that time is relative to the observer. Two people moving at different speeds will literally disagree on what is happening at the same time. My now is not the same as your now if we are in motion relative to each other. If now is not a universal agreed upon instant, it cannot be a fundamental feature of the universe. It must be something local and subjective, a product of our own perspective. The equations that describe reality from quantum mechanics to cosmology do not have a special variable for the present. They describe the entire history of the universe, past and future, as a whole, complete mathematical structure. Physics, it seems, is timeless. It describes a universe that is not a universe that is happening. This forces a dramatic split in how we think about reality. This is the debate between presentism and eternalism. Presentism is our intuition. It states that only the present moment is real. The past was real but is now gone. The future is not real. It is pure potential. This feels right, but it clashes directly with physics as it requires a universal now to be the edge of reality. Eternalism, often called the block universe theory, is the model physics prefers. It states that if now is relative, then all moments must be equally real. The past, the present, and the future all exist simultaneously. The entire history of the universe from the Big Bang to its final heat death is laid out in a fixed, four-dimensional block of space-time. The dinosaurs are not gone, they are just located in a different part of the block. The future is not unwritten. It is simply a region of space-time that you have not yet experienced. In this view, the flow of time is the illusion. This idea is deeply unsettling, so philosophers have tried to find a middle ground. One attempt is the growing block theory. This theory suggests that the past and present are real, but the future is not. The block of space-time is actively growing as the now moment adds new slices of reality. This attempts to preserve our sense of an open, unwritten future. However, it runs into the same problem as presentism. If we cannot agree on where now is thanks to relativity, how do we know where the block is growing? Another attempt is the moving spotlight theory. This theory accepts the block universe that all of time is real, but it suggests that there is a special spotlight of nowness, or perhaps consciousness itself that moves along the block. The future is real, but it is dark and inactive until the spotlight of the present illuminates it. This feels much closer to our experience. The problem is that it introduces a new concept that physics cannot explain. What is this spotlight? What energy powers it? And most confusingly, how fast does it move? Does the spotlight move through time at a rate of 1 second per second? This is a circular definition, a tautology that explains nothing. It merely restates our intuition without providing a mechanism. If we tentatively accept the block universe model that physics suggests, it forces us to reconsider the most personal question of all: who or what are we? Our intuition tells us that we are a three-dimensional being ourself that endures through time. We move from the past into the future. But in the block universe, you are not a thing moving through time. You are a four-dimensional object stretched out in time. You are like a long, complex pattern, or a space-time worm. Your birth is one end of the worm and your death is the other. The you reading this sentence is just one single slice of this complete four-dimensional person. The you from 10 years ago is not gone. That person is just as real as the current you, simply located at a different coordinate in the block. This redefines identity. You're not just your present self, you're the entire history of your life existing all at once. This, of course, raises the terrifying question of free will. If the you of next year already exists, did the you of today actually choose your path? Or are you simply becoming aware of a path that was already fixed in space-time? Physics does not have a consensus on this, but the block universe model suggests that all events are fixed. The feeling of choice may simply be the subjective experience of passing from the cause part of the block to the effect part of the block. This leads us to our conclusion. We are left with two pictures of the world. The first is the psychological picture, a flowing, changing world of possibility anchored by a special now. The second is the physical picture, a static four-dimensional block universe where nothing flows and all events past, present and future are equally real. The most elegant way to reconcile these two views is to accept that the flow is not in the world but in our minds. Consciousness perhaps is the experience of reading the block universe. Our brains are physical systems existing slice by slice within the block. As our brain processes information, it creates a story. It accesses memories information from its past slices and makes predictions information about its future slices and labels the data from its immediate slice as the present. The flow we feel is simply this neurological process, this experience of our individual path through the static pre-existing tapestry of space-time. The universe itself does not need a now. We do. Time in the human sense is not a river. It is the story we tell ourselves about the river long after the water has passed. It is the narrative our minds construct to make sense of our existence within a reality that is far larger and stranger than we can ever truly feel.